Hi, I'm Hafez. I'm a senior data scientist at adjoe, and I've been at the working as a data scientist for more than 5 years now. I've spent the last 2 years at AdTech, and today we are going to talk about deep and cross networks. But before we get to what they are and where we should use them, we should take a few steps back. So bear with me, please. We all know artificial neural networks. They are used everywhere. I think more than 80–90% of everything that is happening at machine learning and AI is doing based on these guys. And their popularity has some reasons. They are based on some simple structured neurons, but you can stack as many of them as you want alongside each other and on top of each other to create a complex network that can solve any problem. And when I say any problem, it's just not intuition or something. There is mathematical hard proof for that. And yeah, this universal approximation theorem is what proves that neural networks, even with one single hidden layer, they can solve any problem to any degree of accuracy that you want. Pretty amazing, right? Although there are some conditions to this theorem that I didn't mention here, but yeah, we'll get to that. So let's see, and yeah, at the top you can see roughly how they do it. So they create many different small linear, if you are using ReLU, for example, they create just small lines that approximate any function that you want. And if you increase the number of neurons, the accuracy would be increased. So let's see how they work on a simple problem, x to the power of 2. You can see here that they are doing a really good job. Here I trained a simple neural network with, I think, less than 10 neurons. And you can see that they are working actually pretty good for the small number of neurons that they get, compared to what usually people use, that is millions, in solving problems in the industry. Pretty amazing, right? But when we move outside of the boundaries of the training data, here you can see within 0 to 10, which was our training data, they are working perfectly fine. But once we move out of these boundaries, you can see that the prediction is diverging from the reality. And this is not good. But if you already knew neural networks and you have worked with them, you might say that, well, isn't this why we have feature crossing? True. First, if you don't know what feature crossing is, it's pretty simple. You just take your raw input features and you make some more complex things, like x to the power of 2, or like multiply two features by each other, or divide one by another. And then you use these features as input instead of the raw ones. So here, if you just take the x to the power of 2, the problem would solve itself. Pretty simple, right? Yes, but there are some problems with feature crossing. First, you need to know this relation exists. If you don't know that your target that you're trying to predict is a function of x to the power of 2, then you have no way to creating that beforehand. Also, there could be a combination of multiple features. Like there could be 5 different features that you have to multiply them by each other, or even a more complex function. So then you can have a meaningful feature that correlates with your target. On top of that, there could be also higher degree of each function. So it could be like x to the power of 2 multiplied by y to the power of 3 divided by another function, another feature to the power of, I don't know, whatever, or any complex function of that. And this is practically impossible. And here is where deep and cross networks come into play. So let's see what they are. We start from simple neural network architecture. I think you probably know this. So we have our input features. Then we have a matrix of trainable weights, which is multiplied by input features, plus the bias. And then at the end, after we did all of this, we just add one activation function on top to create nonlinearity. This is the normal feed-forward neural network architecture. Now, when we move to deep and cross networks, you can see here in the middle, we have the same architecture as normal neural networks. But then instead of having the activation function, here we multiply everything by the input layer, by our inputs. And then we add the previous layer to it, and there we have our output. So let's see what this means. So for example, let's say this matrix here, the weight matrix, is the identity matrix. So here and here and here we have 1 and everywhere else zeros. And for the sake of simplicity, let's ignore the bias and this added input. So what we would have here, it would be x1 or x0, like our inputs, and then the bias is 0 and we ignore that one. So we would have x0 multiplied by x0. So if this thing is the identity matrix, here we would have x to the power of 2, or every feature multiplied by itself. And this is what we were looking for in that problem. But this structure is not limited to this. So you can have any combination, any linear combination of features that you want from this weight matrix, and then, multiply it by the inputs, and you can create any feature crossing that you want. And also, you can stack multiple one of these layers on top of each other to create higher dimensions. This is pretty cool, but you can't use them like this just by themselves. So you need a full structure. Let's take a look. So these two are the most common structures used for deep and cross networks. And here is where the deep comes into deep and cross networks. Let's start by looking at the stacked version. So we start by taking a look at the embedding layer here. We need embeddings. Why? Because usually in our tasks, a lot of features are sparse. We usually use one-hot encoding, and one-hot encoding creates a lot of sparse features that are all zeros. And later on, when we multiply zeros by everything, they destroy everything. So what we do at first, usually we create some embedding layers to make sparse features out of the, make dense features out of the sparse features that we begin with. And if you already have some dense features, you can just concat them. Then we go into cross layers. We stack some layers on top of each other, and the output of them would be the feature crossings that we need. And then we would have our normal deep or feed-forward neural network. And here we have the parallel version. So the embedding layer is the same, but the output goes simultaneously into the cross network and also into the deep network. And once we have the output from both these networks, then we concat them together, and there is one last layer to just calculate the output that we want. Does anybody know what's the difference between these two, or could you guess? Okay, let me save you some time. So as far as I know, from reading the papers and experimenting myself and everything, practically there is no difference. And actually, like, there is a difference, but there is no way to determine which one is going to work best for you. So if you want to use them, just make sure to try them both out and see which one works the best for you. The only difference that you could say they might have is that in the stacked version, because everything goes through here, after you trained your network, you can take the weights from these cross layers, and then you can visualize them. And this way, you can actually see what your model is doing or what features are being combined to each other. So this structure has slightly better interpretability. But other than that, try them out both. So let's see how they perform on the problem that we discussed before. Here you can see that I trained just one cross layer with only 2 trainable parameters, and the results were so identical that I couldn't put them in one plot. I had to separate them out. This is exactly the same. And yeah, the training data was also the same. So I used only this part from 0 to 10 for training. And you can see the prediction is accurate everywhere. But okay, come on. This one was actually like, yeah, this one was a problem designed only to show how powerful these things are. If we want to see the real power of them, we have to move to a real world problem. But to get that, we need to discuss a bit who are we and what we do at adjoe. So at adjoe, we are an ad tech company and we show ads. So we have two sides of business. One side is the applications that are trying to acquire new users, and the other side are the applications that have users and they want to earn money by showing the ads to these users. And yeah, for doing that, we are currently processing more than 600 terabytes of data, and we are doing more than 20 million ML predictions every day. So yeah, it's huge. But what we have to do exactly is to figure out what advertisement is the best for each user. So what we do is we take all the inventories that we have, all the different advertisements that we have, we evaluate all of them to see which one this user would be most interested in, and then we show that one to the user. So yeah, let's see how we used to do it from a technical perspective. So we used to have more than 100 different models. You can see them here. And each model was responsible for one slice of the data. Imagine one model for each advertisement. Why? Because there are different audiences for each advertisement, and normal models couldn't capture the difference between these audiences. So we couldn't just train one model to do everything. We had more than 100 models, and they were using gradient boosted trees, XGBoost to be actually CatBoost to be precise. Yeah, and we used tree networks because we used gradient boosted trees because they are fast. But yeah, one specific problem that this approach had was that we required enough data from each slice to be able to actually train one. If there was a new advertisement or a new slice of data, we couldn't do anything for them until we gathered some data for that slice. So yeah, what we did was simple. We just, actually before we get to that, I'm going to show you how, why we couldn't actually do one model for everything. This is one example of a feature. So we are trying to estimate the probability of a user installing an application here on the y-axis. And on the x-axis, we have how many ads this user has seen previously. So you can see when the user sees more ads, they are less likely to install something. Obviously, because they are now less interested and pay less attention to advertisements, so they have a lower chance of installing. But also we have multiple lines. And here, the blue line is the users who have never installed any apps from advertisement before. But here, the red one, we have users who already installed one application from advertisements. And you can see when a user already installed something from advertisements, the chance of installation is almost doubled everywhere. Also, if they install 3, we can get a double again. If they get, if we get 2 doubled again and 3 doubled again. So you can see how this thing connects to the problem that I discussed before, h to the power of 2. So this is one feature, previous installs that the user had, which multiplies by all the other features that we had and increases the probability. And there is one really interesting phenomena here. So we can obviously see the users who had 3 installs before are the best. They have the highest chance among all of the ones that we show here. But even at their highest points, they are below the users with 2 installs. And this is because we don't have data from the users who installed 3 applications. Why? Because it's obvious. You can't install 3 applications if you already seen only 2 ads. Even if you install all of them, it's not 3. But also, it's really rare that you show 3 ads to someone and they install all of them. So you need some time to gather data for this. But here you can see we don't have any data. So if we had, it would be somewhere up here. But since we don't have it, normal neural networks or any other normal structure would think that actually 2 installs is better than 3. This is the mistake that usually the normal networks would do. But here, deep and like cross layers and deep and cross networks, they don't do the same mistake. So what we did was we trained one deep and cross based model with every data that we had. We just added different slices as one feature. And then it was only one single model giving predictions for everything. And how this changed our structure, or like how this affected us. So the first thing is that this single model could see every part of data. It was trained on all the data, and we know more data almost always means better accuracy or better metrics. So yeah, the metrics overall increased, even for each separate slice. Then we had only one model to maintain, so it was a lot of reduced costs, both from the infrastructure perspective and also from the time that developers had to spend to maintain them. Also, because it was only one model, we could actually batch all of our different like advertisements, all of the requests together, and just run it through the model once. So this resulted in added speed for us. And also, I discussed that we needed some data for everything. So like once we had a new advertiser, we couldn't immediately start predicting for them. But this model, because it had seen everything and it was prepared to make predictions for everything, then we could just start using this model for all the new things. And of course, once we had enough data, we would retrain the model. But this model could predict for everything, so our coverage was increased a lot. Yeah, that's about it. But just one thing to keep in mind here, actually more than one. Yeah. So first, don't overdo it. You might be tempted to like add, I don't know, 10 different layers of DCN on top of each other, because yeah, higher degree is always better. But we have vanishing gradient problem in normal neural networks, but here it's way worse. So in my personal like experience, and also from the papers that I've read, keeping it down to 3 or 4 usually gives the best results. And if you increase the layers, your results will degrade. So keep them around 3 to 4 max. Also, even though they are really fast when you are trying to predict something, once you finish with the training and you want to deploy them in production, but training them is much slower. So keep in mind that you might suffer in that area. And also, there are some other variations. We have GDCN, which is gated DCN. Also, DCN version 3 paper was released, I don't know, a few weeks ago. So this thing that I explained was the second version, which was a generalization of the first version. So, but definitely there are some improvements in GDCN and DCN version 3. So check them out. You can also find the links to these papers here. And thank you. These slides would be shared with you, and I also would be happy to connect or answer any questions that you might have over email or LinkedIn. But if you also have any questions right now, I would be glad to answer them.